Hello, welcome. If you're here, let me hear you in the chat. If I see your name, I get to write down. If I see your name in the chat, I'll write it down and you get your supplemental credit. Hello, Michelle, Crystal, and both Jessica and Jasmine. How's everybody doing today? I love everybody. Son of a... I always get the shittiest thing. No. Hello. Okay, so I'm going to wait 2 more minutes to let people log in, be able to type in stuff. Basically, what I'm going to be going over is just momentum problems. If you guys have any questions on momentum. Oh, shoot. There was a problem she wanted me to go over, huh? Will these be uploaded on your channel after? They should be uploaded. Afterwards, I'm not sure if they will be. Because if the previous 2 sessions aren't being uploaded, then I'm not 100% sure how to do it. I filled around with the channel and it's just not liking me. But I'll try. Oh, it's even wobbly. You should have a knack for picking them, don't you? Yeah. Okay, so first things first, what I want to do is go over any questions you guys might have had on the worksheet that I provided. If you haven't had the worksheet, if you haven't been to my supplemental sessions for the past 2 weeks, then you probably have no idea what I'm talking about when I say worksheet. So just pray and hope that somebody from a previous session brought it with them or something. There you go. Pray and hope that somebody has a question about it. And now I can't remember what problem Dr. D wanted me to cover. Ain't that fantastic? Hello. Okay, so I'm going to be using this. Wasn't it the one you sent us? Was it? I'm not sure. The one that I tried to upload really quickly on... You're part of a search. Oh, yeah, it was that one. Yeah, she never emailed me or anything about it. Great. So I guess I have to figure it out on my own. Use my brain cells for once. Just kidding. Okay. So first things first. Does anybody have any questions on the worksheet that I provided? And if not, what I can do is that I can just start going over some momentum problems from previous quizzes, get you guys busy with that while I solve this other problem. Sound like a plan? Number 5, Giselle. Oh yeah, I forgot. You texted me. I'm so sorry. Number 5. Number 3. Pick number 3, my lord. Okay. So this one is basically a red rock traveling east down a street of ice. Well, I should draw this while I work. Let's do blue for the first one. Or red rock, sorry, it says red. A red rock traveling east down a sheet of ice at 0.36 meters per second. Hold up. I can't remember my groove. Maybe this will work. So here's a rock. And it's traveling east. East is towards the right. This is 0.36. Yeah, 0. Oh my god. I left my coordination in San Diego, apparently. Meters per second. It comes into contact with a stationary blue rock. So there's a blue rock here. And it's not moving. 0 meters per second. Right? So this would be our before session. Before. A. Now our after session is the second half of the problem, in which it says, after contact, the blue rock moves. So we got our blue rock. Excuse me. At 0.14 meters per second at an angle of 67 degrees north of east. So east is going to the right. North of east is slightly up. And that means that this angle here is our 67 degrees. Right? So there's that one. Then we have... No, it doesn't say anything about the red rock. Oh, because that's what we're solving for. The masses of the rocks are identical, with M equaling 18.8 kilograms. Kg. What are the direction and speed of the rock after collision, of the red rock after the collision? So I mentioned this on Monday session, but I know nobody went to Monday session. Just kidding. A few people did, but not everyone had time. So what I was mentioning is that normally whenever you have a problem that kind of like gives you a certain direction and the after part, you can kind of assume that the second one is going to try to cancel that direction out. So what I mean is I think it's going to go southeast kind of. That's my hypothesis. When it comes to all these other momentum problems, basically what I mean is like, oh, you have an object that's like traveling. Yeah, you have an object that's traveling towards this direction, another one that's traveling in the opposite direction. Normally, they're going to bounce off opposite ways in order to cancel each other. That's why usually it's okay to like assume that your second object is probably going to go in the opposite direction of the object that was given to you, in this case, blue. Did that make any sense? I don't know, the one you sent us, I think so. Hey, what do you mean by cancel out? Yeah, okay. So what I mean is like kind of this direction, how it's kind of going northeast. It'll cancel out by this west direction over here. That way, this north or southeast direction. So that way, it's just like the original equation over here. So the north is going to be canceled out by the south, and then that way it'll be purely east, like the way it was before. Not saying that this is the situation every single time, but when you're making a hypothesis, that's usually the way to go. Did that make sense? Yes. So they wouldn't go directly in the opposite. Yes, opposite direction. Yeah, they would go opposite. Not like perfectly opposite, but just enough so that way this will come back. The initial direction will come back. That's how I normally approach it. Maybe you have a different way of thinking about it, but from my experience, it's usually in that direction. Anyway, let's get to solving the problem. We need to find the direction and the speed of the rock, of the red rock afterwards. So we need to find theta red. That is orange. I am sorry. Theta. And then we need to find V final. So right away, what kind of conservation of momentum is this? This is the after. Okay. Can you guys see? Is it blurry? Oh, it's super blurry. I'm so sorry. Is there any way I can make it not so blurry? Yeah, it's an elastic collision. Is this okay? Is this visual okay with you guys? Give it a minute because it usually takes a minute to load. You guys can see? So with elastic, we know that M1, V1 initial plus M2, V2 initial is going to equal the same. Plus M2, V2 initial will equal all the momentum afterwards. So M1, V1 final plus M2, V2 final, right? That whole shebang. What's interesting about this problem, though, is that on top of having to know what was the before and the after section, so the initial and the final, you also have to consider that it's not purely on X and it's not purely on Y. So let's split this up. On X and on Y. What do I mean by this? What I mean is basically our initial momentum right here for red guy over here. He's gonna have a value on X. I'm just gonna leave it all M since they're all the same mass anyway. So M times V1, which is 0.36. Just okay, kind of visible. And we add that to the blue, which is still the same mass, so I'm just gonna leave it in as M times V2. It's not moving on X or on Y, so it's just 0, which means that we can ignore this guy. So swoosh. Let me erase the on Y. It's not gonna fit. Who's messaging me? Don't they know I'm YouTube famous and streaming right now? I wish. And then we don't know the VF, so that's what we're solving for. VF of red. And then the blue one. And we don't know what it is on X. So here's where we have to start using our trig functions. Let's draw this triangle. Do I have a right triangle? That's big enough, right? Excuse me, do you mind? I can't even adjust the size. That's fantastic. There we go. What are you? No. Okay. So this is 67 degrees. We know that this line right here is going to be our V, which was given to us, right? 14? Yeah. Or not 14, 0.14 meters per second, which means that this line here is going to be our X, and this line over here is going to be our Vy. So now you use your trig functions to solve for Vx. So we got to use cosine. I'm just going to skip a few steps because y'all already know how to do this. You have proven it time and time again, and you really don't have to go through the torture. Although it did save me time. Oh well. Cosine 67. And that's going to give us our Vx. Does anyone want to give me the answer? While I set up for y. Vx, anyone? Vy? Oh, it's barely loading. 0.054. Anybody else get that? Awesome. Thank you, Giselle. Right, so now for our equation, we're going to be plugging in this Vx on the Vf portion. So Vx we said was 0.054. Right? Right? Yes. And then, yeah, at this point, you just start simplifying everything. Oh, before I cancel it out, I probably should have canceled out all the m's. So all the m's are going away since we know that they're all the same. And look, there's a 0. 0 won't do diddly squat. Now we have 0.36. Oh my goodness. Don't save it. I need a stylus. 36 is equal to Vf plus 0.054. That is the ugliest 5 I've ever made. I'm so sorry. Or thanks, Alyssa. Did anybody get an answer for VF? I know I stole this from somewhere. Where did I steal it from? I have no idea where I stole this from. Ah, well, let's go. .306. Oh, cool. We still get the same answer. So I rounded it in my original thing as 0.331, but we'll stick to 0.6. So this is our VF for the ball, but this is on X, meaning we still have to find the Y component, right? Right. So let's do on Y. Now this would normally be the part where I tell you guys, you fill it in, and I can kind of see if you guys are understanding. But you're not here, so I cry every time. This one, oh shoot, sorry. On Y, we have M of the red ball, but is it moving on Y at all? Yeah. I mean, I did the same thing when I originally did the problem. I still included mass. No? What happened? Why is Alyssa saying no? Oh yeah, no, it's not moving on Y. No, okay. So when I originally did the problem, Giselle, I also included the mass, but what you end up finding is that they cancel out anyway, and you still get an answer around 0.31. But anyway, yeah, so it's not moving on Y, so that means we have no velocity on Y. Meters per second. Whoop-de-doo, that means we get to cancel it out. And the same situation happens for the second ball. It's not moving, so it's still 0. Now, we have mass times Vy, Vf on Y, but shoot, I should be consistent. Vf plus M, and we said that Vy for the blue ball was 0.128. I'm not even gonna bother with units. I can talk. I don't know what happened to me. I left my tongue at home, I guess. I don't know. But yeah, I'm not even gonna include units because it's taking up way too much time. Anyway, same situation. All the M's cancel out. Swoosh, swoosh. And then we have zeros that basically allow us to ignore them. So now we have 0 is equal to Vf plus 0.128. Right? Wait a minute. Why do I have values? Oh, because I did it wrong. So we're going to end up getting a negative VF. So 0.128 is equal to VF. But what that means is that I drew it going, or sorry. Yeah, so what that means is I'm assuming that it's going downwards like this, right? If I get a negative value, that means that on Y, it's going the opposite direction of what I was anticipating. Or actually, it is going south. It's just going in the same direction. It's direction. I'm so dumb. I am sorry. So let me clarify. So we have north, east, south, and west, right? If we get a negative value on x, that means that my vector will be moving in the negative direction and towards the west. This is negative. If I get a positive value, it's going towards the east. That's a positive value, right? If I get a positive value on y, it means I'm going north. If I got a negative value, it means I'm going south. The only times that it will mean the opposite is if you get a negative angle. So if my angle, when I'm solving for it, so once I plug in all my values for VF on Y and VF on X, I plug in those values, I'm going to get an angle. And if the angle turns out to be some kind of negative, that means it's not going in the direction I anticipated. It's actually flipped. That's what I'm trying to say. But I'm really bad at talking today, and I don't know why. How many people did I lose? Huh? Why? The projector decides to take a break. Doesn't it know that in physics there are no breaks? Okay, cool. Thanks, Alyssa. All right, so let's continue on with the plan. So we're working on red now, so everything's going to be red. We have our VF on X, which we know to be... Oh my god, why? I had to pick the crappiest podium. I swear, it might be special needs or something. Anyway, and then this one is going down. Oh, I had to pick the bad position. Why? There we go. And then straight up. You know, if I actually did something straight for once. There you go. And then, so we have this one being 0.306. There's a point there. Can you guys see again? Cool, you can. So that's V on X. And then we have 0.128. Right? This is V on X, V on Y. Now, I got to solve for V, or VF. That's going to be this guy right here, my hypotenuse. There are two ways you can go about it. The first way is you just use tangent to solve for the angle right here, because don't forget, we're also solving for theta. And we're also solving for VF. So whichever one you want to solve for first, you can. If you want to solve for theta first, you would do opposite over adjacent. Remember tangent, TOA. So you would go tan theta. Tan, oh my gosh. Tan theta is equal to opposite 0.128. I want to beat this thing up. 128, divide that by 0.306, right? And then just solve for theta. And then whatever you found theta to be, you can use that to help you solve for VF. So it'd be like, oh, I found theta to be 36 degrees or something. I don't know. So you go sine theta, or you could go cosine theta is equal to da 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 da, and you solve for VF. That's method one. You could solve for theta first and get your VF afterwards. They should be the same value. If they're not, I don't know what to tell you. Probably means we're off somewhere in our calculations. The second method involves the Pythagorean theorem, where you have 0.128 squared plus 0.306 squared. You solve for that, you end up getting VF squared, and you got to square root that, and then whatever you get is your VF. Then after you get your VF, you would go back, use your inverse function, sine, cosine, to solve for theta. But either way, you should end up getting the same answers. I end up forgetting what the answers are. So, does anybody want to give me a theta and a VF? Got like a 23 degrees for theta. Then I got like 0.33 for hypotenuse. Yeah, 22.56. Yeah, I rounded it to like 23 degrees. And then for VF, I ended up getting like 0.33 meters per second. So are we good on number 5 of the worksheet? My goodness, I'm all over the place. Okay, cool. So that was number 5 on the worksheet. If you're interested in getting the questions on the worksheet and you couldn't make it to either last week's session or to Monday's session, let me know. Shoot me an email. And I'll try to like take a picture or scan it and send it to you guys. Or if worst comes to worst, just like come by the learning center between 11:20 to 12, or not 11:20, 11:30 to 12:30, and I can just give you my worksheet there so you can work on it. I don't know, it's just extra practice. Okay, so let's do a new one. Does anybody else have any questions on the worksheet? If not, what I did for Monday's section is I went over last year's quiz for chapter 9. So I have 2 problems here having to do with momentum. And I can just type those up on the board so that way you guys can work on them while I start working on number 60. Because obviously, if she gave it to me and she wants me to go over it with you guys in class and supplemental, that probably means she wants to put it on the quiz, right? So I'll give you guys these 2 problems as practice. And while you guys are working on it, I'm going to give you guys like maybe 15, 20 minutes, however long it takes me to at least get started on this problem. To get started, and then I don't know if anybody happens to have the answer at that point, that'd be great. See if I can make it bigger. You might need to get that a little bigger, so let me make it bigger. That should be good. Can you see that? Kind of. Let's make it bigger. Bigger is better. Is that better? I wonder if I push you. That will give you guys a better view. Is that good? No? Maybe? I feel like that made it worse. It did make it worse. Can you read that? Oh, it's fine. Okay. So that's the first problem. I'll give you guys, I want to say 10 minutes. Fuck me. There you go.
Oh, I'm so sorry.
Oh, don't worry about
You
it.
scared. Sorry, babe.
It's all good. Don't we need masks? No, you don't need masks because they're both. Oh, sorry. You don't need masks because they're both of similar mass. Says right there of the same mass. So it's gonna be one of those situations where you can cancel out masks. Square. Why do you get that though? Oh, I know why. 2.8 meters per second squared is equal to VF minus VI over T. Change that to VF plus VI over 2. We have 200. And then what we could do here. Okay, well, did anybody happen to find an answer yet? No answers? Oh boy. Okay, well, I'm going to erase this and try to work with you guys. So for those who were in my supplemental during the day, actually, you know what? I'm going to do the problem that she wants me to work on first, so that way the people who already went to supplemental on Monday, they don't have to stick around for the second half where I'm just going to be going over quiz problems because I did that on Monday. So let's do the problem 60 that she wanted me to do real quick. And in case you guys didn't write it down, it says you are part of a search and rescue mission that has been called out to look for a lost explorer. You found the missing explorer, but you're separated from him by a 200-meter high cliff and a 30-meter wide raging river, as shown in the figure. And it shows you the picture of, like, here's the ledge, here's the cliff, and then here's the water, and here's the guy who's on the ledge, not on the water. So from here to here, it's 30. And from the top of the cliff, it's 200. And you got a box here, which is 5 kilograms. And you got a rocket here. which is 1 kilogram. Oh, come on. Wake up, phone. There we go. All right. To save his life, you get a 5 kilogram box or a 5 kilogram package of emergency supplies across the river. Unfortunately, you can't throw the package hard enough to make it across. Fortunately, you happen to have a 1 kilogram rocket intended for launching flares. Improvise it quickly. You attach a sharpened stick to the front of the rocket so that it will impale itself into the package of supplies. Then, fire the rocket at ground level towards the supplies. What minimum speed must the rocket have just before the impact in order to save the explorer's life? So we need to find the VI of the rocket because, spoiler alert, this is an elastic. This is actually a 2-part problem, so let's write this. This is part 1 of the problem, which is going to be all about momentum. And this is part 2 of the problem, which is going to be all about free fall. With me so far? Oh, Lisa got the answers for the billiard problem. Yeah, the theta is 64 degrees, and your final velocity is about 2.3 meters per second. Yes, you are correct. If you have any questions about why that answer is correct, stick around after this explanation, and I will show you. I'm trying to wrap this up because it's already an hour. You guys need your rest. It's been a long, hard week. Anyway, I'm rambling. Let's go. Anyway, so part 1 we know is going to be an inelastic collision because the rocket is going into the box, right? So we know that it's going to be M1 V1 plus M2 V2 is equal to M3 V3, with M3 being the mass of M1 and M2. M3 equals, oh my god, I can't. Here you go. M1 plus M2. Right? We know right away that we're not going to have a value for M2 because the box isn't moving. So we can just ignore that guy for a bit. So what we'll end up having is the mass of the rocket, so 1 times V1, which we don't know. So V1 is equal to M3, which is 1 kilogram plus 5 kilogram, which is 6 kilogram. And then V3, we don't know how fast the two of them combined are. So we still have our V3, right? But we do know that with whatever velocity that rocket and that box are hit, whatever velocity they have afterwards, that's going to be our V initial for part 2. So as that, let me get rid of this. Why did I even? My wrist is already hurting. Oh, so as these guys collide, they're gonna fall, and hopefully they fall to this guy right here, right? What that means is that this transition area right here, whatever VF I get from part 1, it's going to be the same as my VI for part 2. Now let's set it up as if it were a free fall problem. How you guys doing? Oh, boob, Lisa. Eileen. See? Positive support. We're all here for each other. Okay, so let's move down here. So now we have to separate that free fall on X and on Y. Remember that? I think it was chapter 3. On X, we know that whatever our V is going to be, that V is constant. We know the distance in which we need to travel on x, which is 30. We don't know the time. On y, we know you're always going to have acceleration because you're always going to have gravity. 9.8 meters per second squared. You don't know your VI. Actually, you do know your VI on y because it hasn't moved on y yet. So we know our VI is going to be 0. But you don't know your VF. You don't know at what rate it is accelerating. Right? We don't know that one. We do know our height, which is 200. Oh my gosh. I can't write. There we go. 200 meters. And we don't know our time. So the most information that we have is on y, so let's see what we can do to work with this, right? So we have 9.8 is equal to VF, which we don't know, minus 0, which is the VI, I'm going to ignore it, over T. Simple enough. I'm going to substitute for VF, so I know VF is going to equal 9.8 times T, 9.8 T. And then I plug that into that whole equation again, right? So I go VF, which is now 9.8 T, plus 0, which I'm going to ignore because it's a waste of time right now. Divide that by 2 is equal to height, which I do know, on y is 200 meters. Divide that by t. Solve for t. It's looking familiar. 200 times 2, that's 400, is equal to 9.8 t squared. And to save me on time, does anybody know how, can anybody solve for t real quick? $6.39. Thank you. Got 6 seconds. 0.39. Good. Good. And as we know, t on x or t on y is the same as t on x. We could solve for VF if we really wanted to, but what we're more concerned about is finding that V initial, right? And that's going to be on x. So let's use the time that we found. Since V is constant, we know that V is just equal to distance over time. So 30 over 6.39. Anybody want to solve for that? $4.7. Thank you, Cynthia. V is equal to 4.7, right? Hold on. Someone's messaging me. Oh my goodness, I forgot our streak. That's not important. Okay. So we have that V right at the very tippy top of this free fall is 4.7. So that means this is going to be the same as our V final for momentum. So now we take it all the way back up here. V1 is equal to 6 kilograms times, we said it was 4 point what? 4.7? Thanks. Meters per second. And that's going to give you your initial velocity that you need for the rocket. That's like what? 24, 6 times 7, 42, 2 plus 28.2 maybe? Oh, Eileen. The physics is getting to you. It's 30. Where'd you get 30? 30 times 6.39? Is that what this was? No, it's 30 divided by 6.39. .7 seconds. Yeah, divide. Distance over time, remember? And then, did anybody get V1? Because I'm lazy. Yeah, I did it right. Thank you. That helped my self-esteem. 28.2 meters per second is how fast your rocket is going to initially go. Considering that it went from VF of that to a VI of this, that's pretty impressive. But yeah, if she decides to do a kind of problem like this, honestly, the best way to approach these problems is to just write down everything you know. Once you realize everything that you do know and everything that you don't know, you can slowly but surely solve for it. But yeah, so that's pretty much it. The only thing I'm going to do at this point is go over the billiard problem. So the balls. That's only if people want help with that. And if you guys want one more practice problem, I'll type it up right now while people tell me whether or not whether or not they want me to go over the billiard problem. So type in the chat yes billiard or no billiard if you want me to review it. Okay, yes billiard means I will review it. No billiard means I won't review it right now. So I'm gonna type this out while you guys decide. No! Gosh darn it. Oh my gosh, are you kidding me? Okay. Can't see it anymore, so let me make it bigger. That should do it. Gucci? Okay. Okay, can we do the go over how we found VI? Yes, Billy, I understand why we did VI equals max times VX. Same. Oh, yes, Billy, yes, Billy, is the problem for the quiz. Okay. So, yeah, this problem is the second problem from last year's quiz. Arlene, Yvette, I will go back to that problem in just a minute. I'm just going to give like another maybe 2 more minutes so people can copy this down. Unless people have already copied it down, in that case, I'm just gonna move on. But I'll give another 2 minutes. Because it sounds like people want me to go over the Billard problem. But yeah, I'm just going to answer Arlene and Yvette's question, and I'm going to go over the Billard problem. So if you are cool with that and you're down with that, you are more than welcome to just log off, call it a night, maybe study, do any other homework you have. Thank you so much for stopping by on the stream. I might bug you for a signature next week, maybe. I don't know. We'll see when. And I hope you all have the best of luck. Happy post-Halloween. Feliz Dia de los Muertos. Happy All Hallows Day. May the holiest day be ever in your favor. So that way tomorrow you have nothing but blessings. Have a great night. The rest of you, don't leave. I'll still help you. I'll bless you later. All right, it's been 2 minutes. Let's get rid of this thing. Okay, so to answer the question that Arlene and Yvette had real quick, I'm going to draw the thingy again. So the reason why I had V1 is equal, oh shoot, V1 is equal to, is not equal to achoo, is equal to, what did I have? Mass times V3. Did I have mass times V3? I could have sworn everything else was canceled out. Oh yeah, mass. It was 6 kilograms because it was inelastic. So 6 kilograms times V3, which we had to solve. Another way to think about this is the V initial of the rocket, right? You gotta make this small. Let's make it 16. Initial speed of rocket. And that was not given to us because that's what we're solving for. Let's make it 20, 22, 24. Sure, 28 will work. Right, so that's the initial speed of the rocket. And V3, this guy over here, is the speed of the rocket after it's collided into the box. So, of course, after pushing through that box, you're going to have a slower speed. It's not going to be the same as that initial speed. So this is after colliding with box. With me so far? We got this equation because we knew that this whole interaction right here, that, let me get a highlighter, that, can I make it bigger? This whole interaction right here, this right here, that's ugly. That whole thing right there, we knew that was an inelastic collision, right? It's inelastic. Meaning we're going to be using M1, V1 plus M2. Oh, shoot. V2 is equal to M3, V3. Right? So what ended up happening was that we know that this box right here is not moving. So we just ignored that second momentum because, hey, anything times 0 is still 0. Then over here we have the mass of the rocket plus and its velocity. Like I mentioned before, we don't know that initial speed of the velocity. That's what we're trying to solve for. And we are given the mass of the rocket. I just haven't written it down. It's 1 kilogram. And we have 5 kilograms here. Right? And we know that M3 is going to be just the mass of those two combined. So in this case, 1 plus 5, 6 kilograms. If I were to simplify this whole equation, M is just 1 kilogram. So 1 kilograms times V1 is still just going to give me V1 is equal to M3, which is 6 kilogram, times V3. And our job here was to solve for V3 because we know technically you could think of this as the VF of part 1, right? So VF1. And as I mentioned before, we know that once this box gets hit, it's going to go all the way down here. And whatever velocity it leaves this thing up here, that V final is going to be my first velocity on X. That's why I wrote it as VI. You can think of it as VI on X because on Y, you're barely starting to move. Does this make better sense and why we did the whole equation the way that we did? That was beautiful. Thank you. Can you send me the pic? I can't see it. Bless you. I've written down the questions. I can read you guys in a few minutes. If you can, Eileen, because I haven't been saving any of these problems. I'm sorry, Lisa. I failed you. But yeah, Arlene, Yvette, did you guys get that? Oh, I see. I was wondering what happened to M1. Now it makes sense. Thank you. Of course. Yvette, did you get that? Cheers. Okay, cool. So don't save. All right. So if you're cool, down with that, you're pretty much done with hearing me babble. You're free to leave. I'm going to go over the Billard problem now. So if you want to stick around for that, bear with me. Okay. Was it the Billard problem? Yeah, it was the Billard problem. Okay, this one pretty much is exactly like the very first problem that we did at the beginning. So number 5 on the supplemental sheet, but I don't mind going over it. So before everything happened, before the Fire Nation attacked, so I'm just gonna write B. We had ball 1. We had ball 1, and that guy was moving eastward. Right? The bar starting to. Oh no, it doesn't say what direction. So we just gotta assume that it's moving to the right or wherever direction. If you want to say up, down, left, right, just make sure it's consistent. I normally would go with a positive because they're easier to work with. And you have ball 2. That's stationary. We know the velocity of ball 1 is 5.2. And again, velocity of ball 1 is 0. So right away, you know you're going to be able to get rid of this one real quick. After the collision, so they collided, we have the first ball moving 26 degrees with respect to original line of motion. So again, since I drew it going to the right, going east, it's going 26 degrees with respect to the line of motion, so it's going to move upwards a bit. So I have my red ball moving upwards because the angle is supposed to be 26. I cannot today. There you go. There's 26 degrees. No, that's not. I shouldn't be drawing that. There you go. So this is just a reference. It's not an actual vector. Anyway, it's going in that direction, and it's going 4.6. 7 meters per second. That's its VF, right? With respect to original line. I'm assuming elastic collision, a perfectly elastic collision, meaning no energy was lost. You'll worry about that in chapter 10. Find the struck ball's velocity after the collision. So, here's what I mean by hypothesizing the direction of the ball. So, if the ball was moving purely to the right, and I kind of, due to conservation of momentum, I know that it's going to try to cancel out this direction, so that way it just goes back to the way it originally was. So, my hypothesis is going to be that it's going down this way. That's just my hypothesis, though. So again, you have to find angle and magnitude of the ball. So it's elastic. I'm going to be using M1V1 plus M2V2 is equal to the final of all that. So M1 is the same as M2, so I'm just going to write M. 5.2 plus the second ball. Oh my goodness, how did that happen? M2, and it's going 0 meters per second. So we get to ignore them later. Okay. Oh, yeah. Duh, stupid. So let's do this one on X. Because they're not moving purely on X or purely on Y. and the after part. So we got to make a triangle. Yippee. Hooray. I'm so excited. Okay. This is 4.67. That's my hypotenuse is going that way. So this is going to be 26 degrees. I know this is my X. And I know that this is my Y. So we're doing X. 4.67. Cosine 26 is going to give me my Vx. Does anyone know what the value for Vx is going to be? Like, can you solve for it? Because I think Cynthia left and she's usually my go-to person. Cynthia. I always hear people singing that song. I never know where it comes from. I got 4.3. Anyone else get that? Oh, 4.2? Okay, I guess my calculator on my phone's wrong. So I'm going to go 4.2. 4.2 meters per second. And while we're at it, let's just get sine, or Vy. Actually, let me check on my battery. Okay, we're good. That's not X. Okay. And did anybody get anything for Vy? Vy. 2.05? Yeah, looks about right. I have it as a negative. I wonder why. Again, like on X section, we can neglect because one boss only X or Y is going south, therefore it is negative. Wow, me. I sound so confident. 2. I like that. Just agree. Anyway, so you got Vy over here. So M on X was 4.2. So M times 4.2. And then we have Y, or not the Y, the second one, M V final, which we don't know. That's what we're solving for. All right, let's cancel out what we don't need. All these M's are all the same, so I can just ignore them. And then anything that has a 0 is not going to add any value to us. So we end up having 5.2 is equal to 4.2 plus VF. We're trying to solve for VF, so what do you end up getting for VF? This is on X, so it's probably going to be positive. Isn't it just 1? Pretty sure it's 1. So that was on X. On Y, you do the whole shebang all over again. M, our object is not moving on Y at all on the before portion. So this is going to be one of the situations where we can just ignore everything that's going on Y, at least in the initial position. That spooked me. Right, so I have MM. Now on Y, we said it was 2.05. And then we have mass times VF on Y, because that's what we're solving for. Should mention that this is on X. Okay, so cancel out what we don't need. M's are gone because they're all the same. Ignore everyone who's a 0 because they don't add to our data. So what you end up getting, 0 is equal to 2.05 plus VFY. And then this pretty much, it looks like the previous problem when we get a negative 2.05. And that's equal to VFY. The negative just proves that I'm correct in assuming that it's going towards the south. So I draw my triangle again, in which I get something going positively east, so positive on X, and something that's going negative on Y. And I connect the two, right? So this one was 1. I drew such a long thing for a 1. And this one is 2.05. Again, just like the number 5 problem, we got to solve for theta. We got to solve for VF. However you want to solve for it, be my guest. You have creative liberties at this point. Theta should come out to be about 64 degrees. And my VF for ball number 2. So if it helps, you can write 2F so you can identify it. I got it to be about 2.3 meters per second. So yeah, you could solve it however you want. You can use tangent to get your theta, use theta to solve for VF. You can use Pythagorean theorem to solve for VF, and then use any trig function you want to get your theta. It's up to you. So we Gucci on the Billard problem. Oh my God. Are we good? Okay. So if we're all good with this problem, you should not have any issues with the second problem because it's pretty much the exact same thing. The only difference is that instead of working with an elastic collision, now it's inelastic. So you're going to be using the other equation. So you can't really cancel out your m's. But the whole process is still the same. You're going to separate things on x and on y. And then that part 2 is going to be a conversion problem. So I think you guys are fully capable of solving that one on your own. If you do have issues, I will be in the Learning Center, my usual spot, from 11:30 to 12:30, so right before class. So if you guys have any questions, concerns, if you can drop by, bug me for a bit. But yeah, so thank you guys so much for stopping by. I hope you enjoyed. Can you go over really quick the difference between elastic and elastic? Oof, I'm sorry, Michaela, I didn't see that. I'll do that right now. Okay. So basically, the whole ordeal with elastic and inelastic has to do with the idea of whether or not the thing you have one or two systems to begin and end with. So for elastic, my favorite way of remembering it is just if you start with multiple, you'll end with multiple. Elastic. Oh my goodness. I'm trying to be neat. So elastic collisions, which that equation is just m1 v1 plus m2 v2, right? You have your initial and your final. It's going to equal the exact same thing, m1 v1 plus m2 v2. Where really the only thing that's going to change usually is your velocities. So this is your initial here. Initial, 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 your final, etc., etc. So basically what I'm trying to say is it can be a before situation of having two balls. One can be moving, the other one can be moving, and they kind of collide right here. And then the after part, they kind of just, my battery's dying. Hold on, don't die. Don't die. There we go. Still alive. Okay. Okay. Where was I? Oh yeah. So they'll collide. Well, you'll probably get like one guy bouncing. Where'd this guy bounce? He would probably bounce this direction. And then this other guy is probably going to bounce in that direction. I don't know. But they bounce, and basically you get two systems before and two systems after. It can even happen the opposite way. Or actually, no, it doesn't matter. Doesn't matter if two of them are moving, if one of them is stationary. As long as you get two systems before and after, that's an elastic collision. I don't even know if I should go into energy. No, I won't go into that because we haven't gotten to chapter 10 yet. So just keep this in mind that we're assuming all elastic collisions are perfectly elastic. Next, we have the inelastic. Inelastic collisions basically means that you either started off with one or two systems and you ended up with one or two systems. And here's what I mean. So it could be like the coconut problem where you had just one entire system and then it exploded for whatever reason and you ended up with three different pieces going into different directions. I don't know. But what I'm trying to get at is you start off with one system, just the one, and you ended up with three over here, multiple. You didn't have the same number of systems like you did in elastic. You had different ones. Same situation can happen if you were to have two objects, so a ball and a ball. Say it's like going this way, I don't know, and this one's not moving. Say, for example, let's say those two, one of them happens to be like a clay ball or something, and it crashes into it, and they just become just this giant lump, and they're going, I don't know, they're going down this direction for whatever reason. I should make that a bigger lump. They just become this giant lump and start moving down that direction. You started off with two systems, and you ended up with one. This is what I mean by inelastic. So here, your M1 was basically the sum of these three different objects. So 2, 3, and 4. This one, M1, was equal to M2, M3 plus M3 plus M4, right? It was just a collected thing. Now for this one, you had two objects where you have M1, M2, M1 plus M2. That's going to give you that big old mass over here. I'm going to call this M3. And M3 is just the combination of those two together, right? So that's one of the things that makes inelastic tricky, is you got to think of it like that. But the equation, the conservation of energy for momentum that's inelastic, is M1 V1 plus M2 V2 is equal to M3 V3. It's not always going to be in this position. It's just the same. Well, with this one, it usually is because it's reflective. But this one, you can sometimes have your M1, like we had that one coconut problem, equal your M2 V2 plus M3 V3. 2, 2. Does that make sense? Does the difference between elastic and inelastic make sense now? I think your main things that you want to remember for this, though, is these equations. M1 V1 equals plus M2 V2 is equal to M1 V1 equals M2 V2 for elastic, because that's just saying it's reflective kind of deal. And then your inelastic is usually going to be this one. Yes, thank you. Okay, awesome. But yeah, is there anything else that you guys would like me to go over before I sign off for the night? Again, if anything does come up while you guys are studying, or like you just randomly got a physics question in the middle of the night and you need to know before the quiz, you can always catch me in the Learning Center between 11:30 to 12:30, and I'll try my best to help you out right before. Okay? So now I can send you guys off with my blessings. I hope you guys had a happy Halloween and a happy All Hallows Day. Remember, Dia de los Muertos is still going on, so we still have Holy Lands for another 48 hours. I hope that it all falls in your favor, that your quizzes go great, and wish you guys the best of luck. I'm going to delete this. Don't save. Okay, guys, take care. Bye.
I'm tired.